this video, I want to talk about how the neuron resting potential is created and how it relates to concentration differences in some of the important ions involved in neuron function, because understanding the concepts involved in the neuron resting potential will help us understand other neuron membrane potential changes like the graded potentials and the action potentials. So here I've drawn kind of a blown up neuron. So we'll have the soma in red, the axon in green, and one dendrite in blue, and I've blown up the dendrite and the axon really large just so I have some space to draw. It's useful to consider the formation of the neuron resting potential in imaginary steps, but in reality they all occur simultaneously. So first, let's consider a neuron with no resting potential, so it's not more positive outside or more negative inside the membrane, and we'll consider that all these key ions have the same concentration inside and outside the neuron, so that there are no concentration gradients for organic anions, potassium, sodium, chloride, or calcium. Now the neuron is going to be creating organic anions and adding them to the cytoplasm. And as organic anions are being created, most of which are proteins with a net negative charge, these extra negative charges that are being added to the inside of the membrane are going to create a small membrane potential, so that now it'll be more negative inside the membrane of the neuron because of these extra negative charges. But this will be something small, like maybe it'll be somewhere around -5 millivolts. I don't actually know what this would be, but it's going to be some small membrane potential that's not going to be enough for the neuron to function. But even with a small membrane potential, there will now be an electrical force acting on the organic anions, because they will be attracted to the more positively charged outside of the membrane, so that the electrical force will be trying to drive organic anions out of the neuron, but they won't be able to leave, because it turns out that the membrane is highly impermeable to the organic anions. And the same will be true for the diffusion force caused by the higher concentration of organic anions inside the neuron compared to outside the neuron. Even though these electrochemical driving forces are trying to make the organic anions leave, they can't get past the neuron membrane, so they're trapped inside the neuron. So no changes will happen to the concentrations of the organic anions, and no further changes will happen to the membrane potential at this imaginary step. The same is not going to be true for the other ions, because the neuron membrane has channels in its membrane called leak channel or leakage channels. And these channels allow these ions to pass across the membrane, although how easily these ions can cross the membrane through the leak channels is very different for the different ions. And these leak channels are open all the time. They're not gated, so they're not opening and closing in response to some kind of stimulus. For the next imaginary step, let's consider what happens when we add the sodium-potassium pump to the neuron membrane. So this is going to be our sodium-potassium pump. This will be an active ion transporter. It will use the energy of one adenosine triphosphate molecule, that I'll write as ATP for short, to actively transport 3 sodium ions outside the neuron, in exchange for 2 potassium ions being transported to the inside of the neuron. Now by moving more positive charges outside the neuron than it's moving inside the neuron, that's going to make the membrane potential bigger. It's going to make it more negative inside the neuron membrane. I'm not sure exactly what size of change that would be, but it's going to be something small. Let's just say, for example, it might be around -10 millivolts. So now we have a bigger membrane potential, but it's still probably too small for the neuron to function. Far more importantly than this change to the membrane potential, however, is that we're going to have a big change to the concentrations of potassium and sodium inside the neuron. By pumping potassium inside the neuron, we will now get a much larger concentration of potassium on the inside of the neuron than we have on the outside of the neuron. And by pumping sodium outside of the neuron, we're now going to have a much smaller concentration of sodium on the inside of the neuron compared to the concentration of sodium on the outside of the neuron. Now you may be wondering why the concentrations of potassium and sodium changed inside the neuron, but they didn't change on the outside of the neuron. And the reason for that is that the extracellular fluid, all of this fluid outside of the neuron, is huge, And the total number of ions outside the neuron in the extracellular fluid is very large compared to the volume of the cytoplasm inside the neuron and the total number of ions inside the neuron. So that any of these movements of ions across the membrane of a neuron is really going to only change the concentration of ions inside the neuron. And any change to the concentrations of ions in the extracellular fluid is going to be negligible. It's going to be so small it's not even worth considering. There are now opposing forces on the potassium ions. The electrical force will be trying to drive these cations in to the more negative inside of the cell, but the diffusion force will be trying to drive potassium out of the cell from a higher concentration to a lower concentration. At typical neuron ion concentrations at this imaginary step, the diffusion force would actually be much larger than the electrical force. So while there are forces pointed in opposite directions acting on potassium, the net electrochemical driving force, that is the larger diffusion force minus the smaller electrical force, will cause a net movement of potassium ions out of the neuron through the leak channels. As potassium ions are leaving the neuron and carrying their positive charges out of the neuron, that is going to make the inside of the neuron membrane more negative. The membrane potential is going to get bigger and bigger with each potassium ion that leaves. And it's going to continue to do so until the membrane potential is big enough that the electrical force trying to drive potassium ions into the neuron is the same size but in the opposite direction as the diffusion force trying to drive potassium ions out of the neuron. When these forces are the same size and pointing in opposite directions, there is no net movement of potassium ions into or out of the neuron. The occasional potassium ion will wander out or wander into the neuron, but in basically even amounts. For potassium, at typical neuron ion concentrations, this might occur around negative 70 millivolts, which is more than enough of a membrane potential for the neuron to function. The membrane potential, where an ion has balanced electrical and diffusion forces so that there's no net movement of that ion across the membrane anymore, is called the equilibrium potential. It's also called the reversal potential. Now, it actually doesn't take that many potassium ions to exit the neuron to reach the equilibrium potential for potassium. It's something like less than 1% of all the potassium ions in the neuron have to leave for potassium to reach its equilibrium potential, so that the effect on the intracellular concentration of potassium is really negligible. This process does take a little time, though, because most of the membrane is impermeable to potassium, and it can only squeeze out through the leak channels. Now, for sodium ions, both the electrical force and the diffusion force are strongly trying to drive sodium into the neuron because it's a cation, so it's attracted to the negative inside of the neuron membrane, and its concentration is much higher outside the neuron than inside the neuron. If we had a membrane that was only permeable to sodium, these cations would flow into the neuron until so many positive charges entered the neuron that it actually wouldn't be negative inside anymore. It would actually become positive, at which point the electrical force would switch, and it would have to get quite positive inside the neuron for the electrical force to get big enough to balance the diffusion force to reach the equilibrium potential of sodium, which at typical neuron ion concentrations may be around positive 50 millivolts. Without input, however, when the neuron membrane is at rest, the permeability of the membrane to sodium is actually quite a bit less than it is for potassium. And in fact, the permeability of the resting neuron membrane to sodium is something like 4% of that of potassium, so quite a bit less. But because some sodium is able to squeeze through these leak channels, bringing some positive charges into the neuron, that is going to affect the membrane potential a little bit. So that instead of being at the potassium equilibrium potential of around negative 70 millivolts, at this imaginary step it might settle in around negative 60 millivolts. And that's actually a pretty typical neuron resting potential. When the membrane is permeable to multiple ions that have electrochemical driving forces, the resulting membrane potential is a weighted average of the equilibrium potentials of those ions. Weighted by their permeability. At rest, the neuron membrane is much more permeable to potassium ions than it is to sodium ions, so that the resting potential is much closer to the equilibrium potential of potassium than it is to that of sodium. Because the concentrations and permeabilities of ions are usually stable in most resting neurons, the resting potential is usually stable as well. Now neither potassium nor sodium is at its equilibrium potential, however, so there will be a small amount of net movement of both ions across the membrane. A little bit of potassium will be dribbling out of the membrane, and a little bit of sodium will be dribbling into the membrane. This will be matched by ongoing activity of the sodium-potassium pump, which not only creates these concentration gradients in the first place, but also maintains them over time. The resting membrane usually has an intermediate permeability to chloride ions of around 45% of the permeability to potassium ions. In contrast to potassium and sodium, whose concentration gradients play a big role in creating the resting membrane potential, for chloride, the resting membrane potential plays a big role in determining its concentration gradient. The membrane potential drives chloride out of the neuron until its concentration gradient is big enough to balance it, so that normally there's a very small concentration of chloride ions inside the neuron compared to the outside. And because of that, the equilibrium potential for chloride is usually at or close to the typical resting potential for a neuron of around -60 millivolts. Most neurons have other active means of decreasing the intracellular concentration of chloride, though, the main one being the chloride-potassium symporter. And this drives chloride out of the neuron by harnessing the diffusion force acting on potassium ions. So it lets potassium move out of the neuron like it wants to, and it harnesses that energy to also push more chloride ions out of the neuron, further decreasing the intracellular concentration of chloride. Because of this, the equilibrium potential of chloride for most neurons is usually not at the resting potential of around -60 millivolts, but instead it's around -70 millivolts, which will cause some inward chloride flow, leading to a minor change in the resting potential to a more negative value, although usually the change is negligible. Most neurons also have active means to decrease the intracellular concentration of calcium, so that there is a small concentration of calcium ions inside the neuron compared to the outside of the neuron. The main one of these being the sodium-calcium exchanger, which I'll show right here, that drives calcium out of the neuron by harnessing the energy of the electrical and diffusion forces acting on sodium, so that the calcium-sodium exchanger allows sodium to enter the neuron in exchange for pumping calcium out of the neuron. And this creates strong electrical and diffusion forces trying to drive calcium into the neuron. And these forces are so big that the equilibrium potential of calcium wouldn't be reached until the inside of the membrane was around +120 millivolts to flip the electrical force to balance the diffusion force trying to drive calcium into the neuron. But it turns out that the resting membrane permeability to calcium is actually quite small, so that it usually has little effect on the resting membrane potential. So while the concentration gradients of chloride and calcium ions tend to have little effect on the resting membrane potential of most neurons, they do play major roles in other aspects of neuron functions, which we'll talk about in later videos.